If you can see my screen and hear my audio, please type in the comments once. Type Y in the comments. Yeah, okay. So we will start. We were discussing about short time analysis of speech. Short time analysis of speech. So in short time analysis of speech, we are particularly last class discussing about the autocorrelation function. An autocorrelation function is specified for a deterministic signal. Speech is not a deterministic signal, but we have no other option. So we have a random process, and speech signal is a realization of the random process. And there is no other way to extract all the probability distributions and all. How do you find out? It's happening randomly. So we take it as a deterministic function. And why is it short time? There are two things we discussed. One is, I have been speaking about this many times now, short time LTI system and stationary process. So only for small intervals of around 20 to 50 millisecond, you can consider a vocal rack system or voice production system, vocal rack system, whatever you say. That is, you can say more or less it is not, is constant, it is not changing around that interval. So this interval generally comes out in case of voiced speech, in case of voice sounds, around few pitch periods. What is pitch periods? You already know already now. So around few pitch periods. Okay, so during this time, the voice production system is more or less constant. And in those times, and for that short duration, we can consider the speech production system, voice production system, as a linear time invariant system. And in that time, for that small period of time, we can also consider speech as being produced as from a stationary process, or we call that in simpler terms, we call speech as a stationary signal for only that short duration of time. We know speech is a non-stationary signal. We have something like this. We have silence, then we have unvoiced speech, then we'll have some periodic nature, and then unvoiced, and like that. And sometimes there are certain sounds which are called stops, which will be like this. But we have mostly silenced, unvoiced, voiced, again unvoiced, silence, and then there could be some stops and other sounds which are very abrupt in nature and all that. But it's a highly non-stationary, which means its characteristics are varying. Its characteristics are varying with time. With time. But for short durations, if you take a chunk of a signal like that, we can consider it is produced by a LTI system, and we can consider it as a stationary signal. So that is how we analyze speech signal, and that is why we analyze speech signal in terms of small frames or segments. That is why we analyze the speech signal in terms of small frames or segments, because for small frames or segments, our analysis becomes easier. We can consider it as LTI system. We can consider it as a stationary signal, or produced by a stationary process. So hence we use short time analysis of speech. This is the reason why I use short time analysis of speech. Now we are talking about this autocorrelation function. Before we resume that, so I will just talk briefly about this windowing process. So which we were discussing last time. Let's recap. Your speech signal is there, whatever it is, doesn't matter, whatever it is. So let me take another color. So you take a chunk, you take a window. Okay, your window is like this, a symmetric window of some length L, or in time you can say length L means, because these are all discrete time signals. So your symmetric window basically looks like this, but it's easy to visualize, so we don't draw all that circles and all. Yeah, but it's of length L, so minus L by 2, L by 2, or L plus 1 you can say. Indirectly, it's better to say in terms of, speak in terms of time. It makes it our analysis or visualization, it makes it more easier for us. So we take some time duration. Okay. We say, let's say TW or whatever, width of the window, some time duration. So this is your window, and this is your speech signal. Okay, this is your speech signal, this is your window. So you put it here, some value n. Let's put this SM. Let's make this SM. Okay, let's make the independent variable this one. So this is what? This window is now shifted by n naught to the right. So this is your window placed on the speech signal with the center at some value. Oh, sorry, let's put it, I said, so then let's put it n. Okay, so at the place n, we have placed it on top of the speech signal. And now we'll analyze this. So we'll get indirectly this part, and we will do our short time analysis. Now, many things we could do. We'll talk about our autocorrelation function. Then we'll talk about zero crossing rate, energy, and all that. So now you can shift this window. You can shift this window plus by unit sample. Okay, so by unit sample you can shift this window, and then you can do all this whatever analysis you want to do. You can do that. Yeah. But it means a 1 second, let's say a 1 second speech signal sampled at 8 kilohertz. That means there are 8,000 samples in a 1 second speech signal, which is a classic standard sampling rate for speech. So 8,000 times you'll have to do the analysis, and you don't gain much by just shifting one sample. So generally, what is done is shifting by half. Okay, shifting by half the width of the window. Okay, so what is generally done is if you have a window of size of frame size, okay, if frame size frame size some millisecond, let's say 20 millisecond, then frame shift is generally half of depth, half of frame size. So your next window, if this was this one, so you will analyze now like this. So this will be your center point. So again, the other one, there could be another. I will use another color. I think I should. So what happened? So this was your second. Another will be. So the third window will be something like this. So if it was some, if this width was so let's say L, and this was N, this point, so this will be N plus L by 2. L is your basically frame size, frame shift is your L by 2. So this will be N plus L, this center point. These are the center points of the 3 windows. Now there is the advantage of this. There is another advantage of this. Let's talk about it. It's called overlap and add. Sorry. Overlap and add, or OLA in short. So just assume you have a speech signal, and then you took a window, and then you took another window. Okay. So if you take out this chunk, if you take out, so it will be something. Then you process it and whatever. The other chunk will be like this. So if you have different, different frames, you process it individually. Now, if you want to reconstruct, okay, suppose you did not do anything, just broke this speech signal into different frames, and now we have all these signals of different frames, okay, signals divided into different frames. If any two consecutive frames, you just add up like this, based on your what time it is, you see the signal will not be affected, it will remain as it is. The only thing that will happen is it will be scaled by 2. If you add all this, all the frames overlap one on top of the other, so here this portion exactly matches with this portion and this one. So the entire signal, if you reconstruct from its frames by overlapping consecutive frames, you will just have a scaled signal. It will be a 2 times of depth, 2 times of the original signal. So nothing changed basically. The signal remained as it is only by a constant factor. It got multiplied. So signal remained as it is. Now we will talk about different windows in our in this lecture and in the future also. So suppose there is a reason why we use different windows, and windows are a very important part of speech analysis and speech processing in general. Okay, so if we, instead of having this rectangular shaped window, if we had a window which is like this, sorry, just if we had a window which is like this, which is dome shaped. We'll learn about this kind of windows. We have famous Hamming window, Hanning window. We'll talk about sinusoidal, Gaussian, all that. If it was like that, what is the benefit? The benefit is, you see, we want to emphasize the signal that is in the center of the frame. First of all, center of frame, whatever the signal is, we want to emphasize. Why that is important is, see, suppose you have in your frame something like this. So most of your signal is like voiced. But here there is some unvoiced, very little. Why do you want to give equal importance to this? Why do you want to give same importance? Most of your frame is voiced. So you should analyze this as if it is a voiced frame or voice signal. So that is why it's important. The other thing that happens in overlap and addition is that, see here, this I will use another color here, let's say maybe white. So this point, let's say this point, because of this red window, this dome shaped window, it has a value some a. Okay, so what will happen, your signal in the middle will remain but as it is, but it will decrease in amplitude towards the ends of the frame. So it will become amplitude, whatever is your original this one value, let's say some y. So ay it becomes for the red frame. Now for the blue frame, it's again some value b. Okay, for a blue frame, it again some value b. My diagram here, it is not correct actually, because I am trying to visually show, but again by it will be. But if you look, because it is dome shaped, so at any point, this is a, this is b, a plus b equal to 1. At any point, a plus b equal to 1. So when you reconstruct the signal, suppose you did nothing, just divided into frames and reconstruct again from those frames, you use overlap and add, and you reconstruct back. Then you will find, see, a plus b y, it will happen at that point, which is 1. So y, you will exactly get that value. Now, this is why in reconstruction process, overlap and add, in reconstruction process, generally this overlap and add with all these dome shaped windows are used. There are other important reasons why we use this. Apart from emphasizing the signal at the center of the frame, there are other important reasons we'll discuss. But this is why overlap and add is used, generally with 50% overlap between frames. That means if your frame size is L, then your frame shift is L by 2. Or whatever, or if you want to say in millisecond, that's okay. Whatever milliseconds, some t milliseconds or t by 2 milliseconds, whatever, however you represent it in terms of number of points or in terms of time. So during reconstruction, this overlap and add is that's hence used. First of all, we don't analyze the signal for every unique sample shift, because that is too much processing. What will we get by processing the signal? It's such fine resolution. So many samples are there. Even in 1 second speech, it is 8,000 samples. Let's say 8 kilohertz. 16 kilohertz means 16,000 samples. So we do a trade-off. So we do a frame shift, generally half frame shift, if we are doing reconstruction. If we are not doing reconstruction, only our aim is to analyze the signal, then we could go for maybe 75% overlap or even 25% overlap. All those things we can play with. But for if you have to reconstruct back the signal from its frames, then generally 50% overlap is what we need to do. Now, I will give an example where this might be, you will get a better visual interpretation. So I am saying that if you just have the speech signal, you broke it up into multiple overlapping frames, and suppose all those frames you did nothing and just reconstructed that. Now assume the speech signal was corrupted with noise. The entire speech signal was corrupted with noise. You were recording and there is lots of background noise. So obviously what we will do is you break the speech signal into frames. Each of the frames, you will use some algorithm, some denoising algorithm to get a clean estimate of the signal as far as possible. Let's assume this is a perfect algorithm and you got the clean signal. Now you use this overlap and add, and you will get back your original uncorrupted speech. But this is a simple example. This is called speech enhancement or denoising of a speech signal, where you will see overlap and add being used. But overlap and use is used in many everywhere. It is used, particularly where reconstructing the speech signal is necessary. So now coming back to topics, so we discussed about short time analysis, how windowing is used, overlap and add. Now let's go back to our original thing, autocorrelation function. So we'll discuss about all that short time autocorrelation function. So we know what short time analysis, why we use, and autocorrelation for deterministic signals. We talked about it last time. So basically you have let's take the index M. You have your speech signal SM. Okay, let's put it like this. And if you have a chunk, you took a chunk of this. Now this chunk could be by a rectangular window, or it could be by a dome-shaped window. Okay, does not matter. But let's assume a rectangular window for our purpose. Okay, let's assume that we have a rectangular window. So in the rectangular window, now you have your signal like this. Something like this. So this signal is what? You put your rectangular window at a position some n. Some position n. So S, M, and W, n minus m. Okay, because a rectangular window is, this is your rectangular window. This is how your rectangular window is. So if you basic signal processing operation, this will be the representation of your. So we can say this is SNM. And what is your objective? We will now slide this shift this signal by certain amount. Some M naught something, some L, let's say some L. So what will happen? You see, it is not matching. So if we do this and we multiply and get the inner product. So you have Rx or Rs, whatever you, this R of L. It is SNM and SNM minus L or M plus L, whatever you way you want to represent a shifted signal. SM minus L will be more correct. Okay, you shifted it, or oh sorry, here I think it's better to write M plus L. Yeah, this will be the correct one. So if you shift it and then multiply it, what will happen? See, for some, whenever, see, these peaks are matching, where L is equal to 0, this is nothing but your energy, because it is like square. This is your energy when L equal to 0. When this peak again matches this, then for that value of L, there will be a high value. So finally, you will get, in terms of L, energy, something like this. Sorry. Energy, something like this. Or N naught, you can say. So what you will notice that at a particular value N naught, you will get peaks. This is nothing but your pitch period. If you convert this N naught, these samples into equivalent time, is N naught, what will you do? N naught into TS, sampling rate. Okay, if you convert this into a time, this will become your, in millisecond or second, your pitch period. Okay, this is a pitch period in terms of number of samples. This is your, in analog domain, how will you represent? So this is your pitch period. That is how we find out our pitch period. Now, had that I told you last class, that had this been a perfect deterministic signal instead of our speech signal, had it be a sinusoid, then all these small peaks will not appear. It will be like a perfect autocorrelation. But since speech is not a deterministic signal, even though we take small segments and consider it to be deterministic, so you will get some peaks and all that. But you'll find that there will be always large peaks. You can easily discriminate them in case of voice speech. And that is how, using this small, easy process, time domain, short time domain process, we can find the pitch period of the signal. So let's see, for example, here. This is a 30 millisecond. See, 30 millisecond speech, a voiced portion of a speech signal. Uh-oh. Yeah, so this is a voiced portion of a speech signal. Anyone? What happened? Somebody is facing internet issues. Okay, this is a voice portion of a speech signal. A color of 30 millisecond. Okay, where is it again? I went back. Yeah, this is a 30 millisecond duration voice portion of a or voice frame of a speech signal. So if you see the autocorrelation function, this lag is represented in terms of millisecond. Okay, you will see peaks are there. Now you can see from this, where is this? This is the pitch period. You can easily see from the waveform itself. So this is, for example, around, I think, some around 2.5, and this is something around 11.5. So around how much it is? Around 9 millisecond is a pitch period. You can see there is a peak at around 9. Again, there is a peak at around 18. Now you can do a little bit of post-processing of this autocorrelation function to find out your pitch period. You can smooth. One way is to smooth it. Means you take a simple rectangular function, rectangular window, or any other symmetric window, and then average the values for that width. Then you can again shift by one sample and average, and so you will get a more smooth kind of. You can smooth this. This process is called smoothing or moving. This is also called moving average filter. Moving average filtering. Okay, and then you can these small peaks, they go away then, and you are left with only peaks at the pitch periods. Or you have other option. You can take these points, all the peaks, and fit a curve, fit a 2-degree quadratic or 3-degree curve, and then also most of these unnecessary peaks will be removed, and you will be having those important peaks. But this post-processing you can do. But the basic thing is the autocorrelation function. The autocorrelation function helps you find out the pitch period. And the basis for it is because we can see from a deterministic signal, if we shift it, a deterministic signal having a particular time period, then peaks will occur at the autocorrelation function at this particular time period. So that is the principle behind it, and we use that principle for short segments of speech. Now, moving forward, now let's see, this is your unvoiced speech. How does the autocorrelation function look for unvoiced speech? If your frame is unvoiced, if your frame has got unvoiced speech, see how the autocorrelation function looks like. There is no peaks that you can easily find out, that you can easily discriminate. So this is how autocorrelation function of an unvoiced speech looks like. Unvoiced speech is generally, it looks like noise, and the autocorrelation function also looks like noise. So then let's look at what happens. So you have a speech signal, is some sentence you uttered, something you spoke, some sentence you uttered. This is a recording of that, some phrase. And then you do frame by frame analysis. You do frame by frame analysis. Okay, these are all frames, and the center of the frame, it is represented by this time. Okay, whatever center of the frame is, it is represented by this time axis, nothing else. You could also shift it. Now here we are not worried about reconstruction. We just want to find out pitch period. You can do even one sample shift. There is no problem. Or you can do your classic 50%. Or you can do 25%, 75%, up to you. Because we are not concerned with reconstruction here. We are just trying to find out the pitch, analyze the signal. So this is the time of the center of the frame basically. So and then wherever it is voiced, you can see, you can say clusters. Wherever there is voiced frames, there are clusters of pitch. Wherever there is unvoiced, you will see all these random things come up. If you use the autocorrelation function and try to find out the peaks, distance between the peaks, then you will find all this high energy, some nonsense will come up. These are unvoiced, but wherever they are voiced, you will see consecutively you will find values which are consistent. So I talked that for adult male, the pitch period is generally around 100 millisecond. Sorry, pitch frequency or fundamental frequency or pitch frequency is around 100 hertz, and on a female it is around 200 hertz. Okay, so here they are plotting in terms of frequency, fundamental frequency or pitch frequency. You can see around 100 hertz you have. So this is most probably a male speaker. If it was around this region, 200 hertz, that would be most likely of adult female speaker. Children would be much higher. So that's how you can, this is called a pitch contour. You can analyze the pitch variation. You can what is called find out the pitch for the entire speech signal in this manner. So now coming ahead, we discussed. Yeah. So next thing in this, let's go for in terms of short time energy and zero crossing rate. So in short time analysis, first thing I talked about this autocorrelation function mainly because I discussed how speech is a random process and why it is a random process, but why do we analyze it in a deterministic manner and all that. So I started with autocorrelation function. But there are certain even more easier but very effective short time analysis things, methods or techniques that we regularly do in any speech processing activity. We have to. So that is by energy, short time energy and short time 0%. So what is short time energy? You put whatever window you want, mainly dome shift. Why? Because let's say this is unvoiced and then your voice starts. So if most of the frame is voiced, why do you want to give equal importance using a rectangular window? Instead you use a dome shaped window, give emphasis to the center of the frame. Or there is another thing, suppose there is some abrupt sound is there, some stops or something, some abrupt activity, abrupt change is there, and this is your frame. Why should you give importance to this certain abrupt activity? It might be due to recording, it might be due to background or something. So to remove all those, it will also, of course, it could, some abrupt activity could occur even in the middle, but at least towards the ends we could get rid of them. So anyhow, so whatever window you use, now autocorrelation function at zero lag is the same as energy. So it's basically what you have S and M. What is S and M? I just talked. This is your energy. This is your energy. Now you plot this energy for, you could have your again, this is analysis for so no need to go for OLA and 50%. You could do different kind of overlap, 25%, 75%, or even single sample by sample shift. So you can plot this energy. Okay, you can plot this. This is your time, and you can plot this energy. So what you will find that wherever this is voiced, you will have high energy, and wherever it is unvoiced or silence, low energy. Silence or unvoiced will be low energy. Wherever there is voiced, will have high energy. Generally, voiced will have much higher energy than unvoiced, than silence. But this is for clean conditions. But if your signal is having some amount of noise, then this silence and unvoiced, it becomes difficult to discriminate in terms of energy. But if it is a clean, then more or less voiced, unvoiced silence in a good way it is. You can discriminate. At least under any circumstances, voiced, you should be able to discriminate from unvoiced and silence. So this is a simple technique. Now, along the same lines, we can have this zero crossing. So zero crossing, let's see the funda of zero crossing. Funda. Let's say 1 second, you have a sinusoid, correct? So how many zero crossings are here? Is a sinusoid of 1 hertz. So 1 cycles per second. So how many zero crossings? 1. Now suppose there was a 3 hertz sinusoid. How many zero crossings will be there? 5. Now you can check like that. You can keep going. So if you have 6 hertz, you will find that it will be it's called 11. So, but approximately you can say it is twice. The frequency is twice the number of zero crossings. So the same thing, what we are seeing in a deterministic signal, like a sinusoid, we want to apply for a what is called for a speech frame. So what we will do is, for any speech signal, frame by frame, for every frame, we'll find out the number of zero crossings. And how does it help? You will find, obviously, see, unvoiced speech is like that. Silence also, silence amplitude is very low, but you will find that a lot of zero crossings happen. But in case of voice speech, you will not get so many zero crossings. So zero crossings for voice speech is low compared to unvoiced and silence. High. Now you can use both this energy plot, energy fun, that you compute, and zero crossing, and combine both these two metrics to get a very good demarcation of voice, unvoiced, silence. Now, at least you should be able to get a good demarcation or separation between voiced versus unvoiced and silence. Unvoiced and silence, to demarcate them, it is a bit more tricky in the time domain. There are other methods using frequency domain also, but at least voice versus unvoiced and silence, you should be able to quite quite satisfactorily demarcate or differentiate. So now how to find out the zero crossings? Uh, is a simple method. See, so uh, signum function or sine function basically. Okay, it is like this, but let's say sine functions. The sine function is what? If your number is positive, it will give 1. Okay, let's greater than equal to 0, it's 1. Less than 0, it's, you can put it 0, -1, whatever you want. Okay, let's say -1. Okay, less than 0, -1. Signum function, the signum function is continuous, it's like that. In discrete time, we call it the sine function. You can say 0 is, you can put it as 1. Or you can, yeah, or you can put 0 as 0. Greater than 0 is 1. And less than 0 is -1. That's also fine. In discrete time. Sine function. Okay. So whenever you have something like this, a zero crossing, the sine function will give 1 here and -1 here. Then there is another type of zero crossing. And it is moving like this, -1, 1. So if you have signum function x of m, or s of m, I will say, minus s of m minus 1, what will you get? You will get either 2 or -2. For other cases, you will not get. For example, here and here, if you take 2 consecutive samples, and you will get 0. So only in this case of zero crossings, you will get some value 2 or -1, or -2 or -2. So you use this. So if you take 0.5, it will become 1 or -1, and then you use a window function. You are evaluating this for a particular window. Okay, so you can put here SNM, SNM -1, like that you can put, or indirectly you can say that signum of S of m minus signum of S of m minus 1 Wn minus m. You do 0.5 and you sum it up. Sum up this for that frame. So you will get the number of zero crossings for that, frame. That's how you'll get the zero crossings for that frame. Then you plot it. So let's go back. So this is how it is. That's what I was saying. Signum of xm, signum of xm minus 1, 2 consecutive points. This window function, it means for a particular frame you are evaluating 0.5, so that instead of -2 and 1, you will get 1. Okay, modulus is there, so you convert it into a positive number. And this is how you get the number of zero crossings. So here they have used sign of or signum as x greater than 0, but you can also, yeah, you can use this, but you can also use 1, 0, and -1. It won't make much of a difference. So this is how you evaluate the zero crossing rate. So for voice region, high energy, low zero crossing; unvoiced, low energy, low zero crossing; even silence, low energy, high zero crossing rate. So let's look, for example, I have a figure here. This is your time. This is your time. Basically the center of the frame. See the zero crossings, how it is. These are all unvoiced regions. Very high. Very high. These two are windows. This a particular Hamming or Hanning window. They have a dome-shaped window. They have used. Forget about this. What the shape of the window. This red line, green line you see, and the energy. On the other hand, see energy is quite low compared to your voice region here. You can see voiced. It is periodic. You can see the structure itself. So you can combine these two parameters and use a thresholding. You will have to evaluate the threshold by statistically or by manual input. Okay, you can use your threshold, and then you can find out which frames or which segments of the speech signal are voiced, unvoiced, silence. So these are the uses of energy and zero crossing. Speech endpoint detection is voice unvoiced speech detection. Speech endpoint detection is nothing but you have the speech signal. Where does the speech signal start? You have the silence, then you have generally unvoiced, voiced, and then again this unvoiced and silence. This is how a speech signal generally is. So you want to mark the ends of the speech signal. So I did not speak about why is it necessary to mark voiced, unvoiced, and silence. Why is it necessary? So the reason is when you for any speech application, we are always trying to reduce the computational burden, computational complexity. Reduce the computational complexity. Why should a machine, why should a program analyze silence if it is not necessary? Why should a machine analyze unvoiced if for that particular application it is not very useful? Silence in no application. What is the use of processing silence? You will give, if you process it, it will give garbage results. Similarly, there are many applications, for example, speaker recognition, where unvoiced is also not useful. Only the voiced are useful. Other applications, for example, speech recognition. You don't need silence for any. Why will you process? No application requires silence basically, apart from a, speech enhancement. They use something called adaptive signal processing. They need statistics of noise. That's a different thing. But more often, you don't need this silence. And sometimes you don't even need the unvoiced. So if you can find out which of your frames are voiced and unvoiced, or which of your frames you need, then you just don't need to process all the rest of this, the rest of the frames. You can see for a simple speech signal you record, there are thousands of frames. Out of that, many hundreds you can just simply discard. Then you can save your computational time, computational resources. So that is why we do this voice, unvoiced, and silence classification. That short time analysis that we use, zero crossing and energy. It is very it's called a simple method, very efficient method, particularly for if the speech is not corrupted by noise. But if it is corrupted by noise and things like that, then we also have to use other techniques, maybe some frequency domain techniques and all. These are all open-ended research things. It always goes on. What is the best method that gives delta performance improvement in discriminating voice and voice speech, the best method of endpoint detection. These are all evergreen topics, research topics. So What I will do now, I will give you a little bit of a break. A little bit of a break. We'll meet 11. Let's meet at 11:10. Oh, let's start. If you're able to see my window and hear my voice, please type Y. Okay. Now we'll discuss something very important conceptually. So please pay attention. So till now, in short time analysis of speech, we are doing short time analysis of speech. We have talked about autocorrelation function, energy, zero crossing rate. These are all time domain methods or time domain processing or time based analysis, time domain analysis, time domain methods, time domain analysis, time domain processing, whatever you say. Now we will look at something, frequency domain analysis. So we have seen this time domain analysis. Now we'll do frequency domain analysis, and we'll discuss the importance of these windows, different types of windows. We'll discuss short time Fourier transform and the spectrogram. So let's first start with what is the effect of this windowing. Okay, and even before that, let me start with stationarity. Okay, so suppose you have a sine wave. Okay, and then that sine waves suddenly changes in frequency. So if you have a infinitely long sine wave, let's say this is 0. On one hand, let's say there is some frequency f0, and on the other side you have 3f0. Now if you do a Fourier transform of this, what will it look like? You will find two impulses at f0 and 3f0. But is this the true representation of the signal? Is this the true representation of the signal? That's the question. If you had another signal with f0 and 3f0 and they are summed up, so your result will be like something like this. This will also give the same result. So why is it important? See, the important comes here is, see, this signal is not stationary. Its characteristics are varying with time. This signal is stationary. So at any point of time, you have this signal. This signal is a combination. This signal is a combination of all these two sinusoids. But here, this signal is not a combination of f naught and 3 of naught at any point of time. So this is where this, and that is why this windowing becomes important. So in our speech, we have different kinds of waveforms at different portions of the speech signal. Hence, we need to window them and analyze them differently. This is the reason, so that your Fourier transform is valid. If you take the Fourier transform of the entire thing, it is like an invalid analysis. If you take a huge window, because what is happening, what it means that whatever your spectrum comes up, that means all these frequencies are presented across the whole signal time, across the entire length of the duration of the signal. But that is not true. The signal is varying with time. So this is the limitation of Fourier transform. It is not valid for non-stationary signals. And that is why this is another reason, apart from you can do long-term, a short-time LTI system, that is also required for Fourier. Okay, but the stationarity, we can assume the signal to be stationary only for short intervals of time, and then only Fourier transform will make sense. Otherwise, this entire spectrum, you will get lots of incorrect information from the spectral analysis using Fourier transform. So now, once we do windowing, so let's get back. I should not forget Fourier transform on, yeah. So effect of windowing. Let's talk about the effect of windowing. So we have signal something like that. We put a window. It could be any window. Let's say a rectangular window we have put. So windowing is not just without any disadvantages. So to understand that, let's take a sinusoid. What is the Fourier transform of this sinusoid? If it is infinitely long, you can check from your if it is f naught, so that is 2 pi f naught. If I am saying this omega, okay, there is an impulse at that point, at that particular frequency. Now suppose you took a chunk of that, what will happen then? And then took the Fourier transform. If you took a chunk of that and then did the Fourier transform, what will happen is you will find the spectrum becomes something like this. This is a magnitude spectrum, okay? I'm just plotting the magnitude. This is called spectral leakage. See, you are getting unwanted things. And there is instead of an impulse, there will be a lobe, big main lobe. And these are called side lobes. Main lobe, side lobe. Now, why does this happen? So we had, if we take an infinite sinusoid, sine omega naught t or cos omega naught t, You check your revisit your Fourier, let's say n. Revisit your. I'm sure you're revisiting your signal system. You will get at omega naught or 2 pi f naught, whatever. An impulse there, and also minus omega naught. Let's forget about it. Let's talk about only the positive spectrum. But if you truncate it, if you put a window, then your spectrum becomes something like this. This is the effect of windowing, and why it happens. Let's talk. So let's say this is xn. So, or yeah. So I will again use m as the index. Okay, m as the time axis. So let's say this is. So the windowed part, if I take this as m, will be like this. You can represent this as x and m. The windowed part will look, this is the representation. Now, if you go to standard Fourier, go to the multiplication property or modulation property. So if you have, we have x of m, wn minus m, which we call at x and m, that means your center of the frame is at n, we'll have x e to the power j omega convolution with w e to the power j omega. So if this is your window, which we call a rectangular window, a particular length, it has something called as a sinc function, a lobe. It has a Fourier transform like this, and you have your xm. In case we are talking about the sinusoid, which is having at omega naught. This is 0. The result of this convolution will become that this will just, wherever there is an impulse, it will just replicate it there. So the result will be omega naught, this will come up. So this is the effect of windowing. So this causes, effect of windowing is spectral leakage. So the true spectrum is distorted now. Instead of having an impulse at omega naught, it is having a main lobe and some side lobes. The spectral leakage, and all this is determined by the length of the window and shape of the window. Shape of the determines how much spectral leakage, what is the height of the main lobe, what is the width of the main lobe. Okay, so what is the side lobe level, width of main lobe, height of main lobe. All this is determined by the length and shape of the window. And we'll discuss about different types of windows hence. But I hope you got it, what happens when windowing occurs. Now, let's assume, now we cannot do, in speech, we have no option but to, there is no option, we have to put frames because it's a non-stationary signal, and only for short durations we can consider it as stationary. But you have now this signal only. So what will be the effect of windowing will also be felt here. Suppose you knew the actual spectrum of the signal. Suppose you knew the actual spectrum of the signal S e to the power j omega. We, we never get to see that. We'll always get to see this S n e to the power j omega. But suppose you had access to the actual spectrum of the signal. It is having the effect of windowing. It is convolved with the Fourier spectrum of the window function, and that is what we see. Now, let's go back to some simple things. Suppose you had a single impulse function. A single impulse function. Then your Fourier transform will be like everything. Minus pi to pi. Everything is a flat. As you increase this width, it decreases. As you keep increasing, now if your window becomes infinite, it becomes a unit, this one. So if your window had been infinitely long, this becomes an impulse function and you will get the exact. But you cannot have an infinite window because then because your speech signal is varying. So you never have access to this original Fourier transform of the speech segment. But imagine that you are speaking, let's say a vowel from A, let's say, and you're speaking for 10 minutes. Like that. Just then you could imagine these are infinitely long, and if you take the Fourier transform, okay, Sn e to the power j omega equal to, then you could have this will be, because it is so long, you can take the entire duration, 10-minute duration. Wow. So this will be more or less like a sharp impulse, and you can more or less say Sn e to the power j omega is what we have got is original actual spectrum of the signal. But obviously in continuous speech we cannot do. So always whatever you get is a convolved or convoluted spectrum. Now let's so I hope that is clear. So let's talk about now what is the effect. Means I've talked about already. Let's see this. So here is this simple example of a sinusoid. Okay, it is a 13 hertz, I think, 13 hertz sinusoid. And discrete time Fourier transform you took, you see, you get at 13 hertz, this main lobe and side lobes and all that. That's what I was saying. Yes, so now let's go to short time Fourier transform and why is it helpful and why is it not? What are the trade-offs we have to do? So we just talked about this. We use, if we have SNM, what is SNM? This is your windowed part. So short time Fourier transform is that windowed signal, that frame, you take the Fourier transform. That's it. This part, you know, this is the window, and you take the Fourier transform of that. And what is the result? You have this convolution with, as we talked, we have this convolution with the window. Now, let's imagine, let's talk about what's the effect of this type of convolution. Okay, so here is a good example of what is happening. Okay, uh, uh, let's take this. Will become a little bit clearer when we talk about source filter theory in the coming classes. In the next class, or maybe next class, we'll discuss it. So in case of voice speech, you see we have the glottal cords that vibrate. We saw engineering diagram like that. Okay, and you have your mouth, nose, mouth, glottal vibration. Okay, and then this is your airflow and all. So, and I told you that when you have tubes like that, it causes resonance. It causes resonance when you have tubes like that. That's why we studied. I asked you to revisit what is a resonator. Okay, in signal processing terms. So generally, in case of voice speech, your spectrum will be something like this. So this spectrum, what you will have, you will find some high regions. Some if you take this spectrum, okay, magnitude spectrum, you'll find there's some regions. If you trace the envelope, okay, there will be something like this. But if you these small peaks and valleys and all that, but if you trace the envelope, there will be certain high regions. These are because of the resonance or resonators. We discussed about it, what happens when there is a resonator, how the frequency spectrum looks. These are because of the resonators. And uh, these small peaks that you have, these are basically because of your vocal tract, glottal vibration or vocal fold vibration. The vocal folds are vibrating at a particular rate, particular pitch, frequency, or fundamental, and these peaks represent that. We'll discuss about this in source filter theory in the coming class, but just take it from now that a speech waveform or the spectrum of the speech for voice, it looks something like this. You will have, these are called vocal tract resonances at particular frequency. Okay, generally for every 1 kilohertz, there is a vocal tract resonance or a foreman. In case of unvoiced speech, and you will also find in voice case that there is a slope. That means F1 and this spectrum is high in the low frequencies and it gradually decreases as the frequency increases. In case of unvoiced, however, the opposite happens. Generally, there are some vocal tract resonances, but they are high at high frequencies, not their magnitude increases with frequency for unvoiced speech. And you do not have, because there is no vibration, you do not get this kind of peaks at regular intervals. It's a zigzag kind of pattern. There is no regular structure, but you can still from the envelope see that there are certain high regions which increase with frequency. You can check in Audacity, you record your voice and find out all that. Experiment with yourself. So now short time Fourier analysis, let's come back to that. So if you take a long, okay, a long window, Suppose you have a voice frame and you need a window length, you took a long window length. What will happen is if this is long, then the window spectrum, okay, that will become narrow. It becomes narrow. Okay, length, that spectral bandwidth, we call this bandwidth of the spectrum, it will become narrow. And then when you convolve it, so you can see these peaks. If you measure the distance between the peaks, these peaks actually come at this pitch frequencies 2f0, 3f0. All these peaks will come at this will be there at this pitch harmonics. We call this pitch harmonics. That means integer multiples of some integer multiples of the fundamental frequency or pitch frequency. On the other hand, if you take an only short slice, okay, in the previous case we took some sorry, in the previous case we took some you can see some pitch periods, some few pitch periods we took, 4 pitch periods in this case. That was the length of the window we consider. Now let's take a very short window. So as the length is decreasing, in inversely proportional to, your spectrum of the window will be very wide. And when you do convolution is type of a moving average window. So all these small fluctuations that were there, those will be averaged out. You will not see. The only things you will see now clearly are the formant frequencies, the positions where their vocal tract resonances occur. So this is where this choosing the window, choice of window length becomes critical. So if you want to find out and analyze the pitch harmonics, their length should be more, window length. On the other hand, if you want to analyze the spectral vocal tract, the spectral envelope, it is called the spectral envelope, and determine the formants or vocal tract resonances, then you should have a short length window. So based on this, we have what is called a spectrogram. Based on this knowledge, we have what is called a spectrogram. A spectrogram is nothing but a periodic representation. Okay, before that, okay, since we are talking about windows, let's complete this part, windows. So we talked about rectangular window. Oh, sorry. So we talked about rectangular windows. But I said there are more better windows or other windows which are used for various purposes. Two of the famous are Hamming and Hanning, or Hamming and Hand. This is the equation. So they look like this. Okay. So here is 0 to n they are putting, that means 0 to n, but of course you can shift it and make it centered around 0. Okay. So when a naught is 0.5, so it will become 0.5 1 minus cos of 2 pi n by n. Then this is called a Henning window. When a naught is 0.54, if you put 0.54, so this becomes 0.46, then it becomes a Hamming window. So, and what are the advantage? Lower side lobes. Primary advantage is lower side lobes. Disadvantage is loss of frequency resolution. I will explain that what it is. So let's first look at this rectangular window. The rectangular window, it's the samples, the n samples, and this is one unity. This is a Fourier transform looks like this. Here it is mentioned in terms of frequency beams. You use DFT in reality in MATLAB or other software, but that's so you calculate number of frequency beams. But better to put it in frequency terms. But okay, it's like that here. So there we have a bandwidth here. That means is width of this main lobe. Okay, and this is decibels, means your magnitude spectrum. This is 20 log 10. That's what it is. dB. So when you do 20 log 10 of the magnitude spectrum, it looks like this. Again, you can see the effect clearly. Okay, the side lobes and everything. These are the side lobes. This is the main lobe. So you can see here some b equal to 1.0 something is mentioned. So does not matter. So the main lobe width is narrow, but there are lots. The side lobe values are also significantly high. Now, if you go to Henning window and compare with the rectangular window, you see the side lobe levels are significantly less than rectangular window. The disadvantage is that this increases a little bit. Again, you have a Hamming window. Its beam width is, I think, yes, it has a lower. It has more what is called bandwidth than the rectangular, but you will see uh, its bandwidth is greater than rectangular, but it is lesser than this. It is lesser than this Henning window, but this trade-off is that its side lobe level is also high. But in any case, the side lobe levels of all these Hamming and Henning windows are lesser than rectangular window. The trade-off is their main lobe is wider than that rectangular window. So that is the trade-off that these windows allows us. There are many windows. It's an open area research. There are a huge number of windows, and they have all different properties used in different applications. But in speech, these three windows, Hamming, Henning, and rectangular, are the most widely used, and hence I am projecting and showing them to you here and what's their purpose. So now let's come to STFT, spectrogram. So let's come to spectrogram. So what is happening is if the speech signal is divided into overlapping frames, for each frame, so you can put a the center point, or you can put even the beginning edge. You can either put your beginning edge or either center point. You can give you a time axis. Okay. Then for each frame, you will get a spectrum. Each frame there is a spectrum. If this is the frequency axis, omega, there's a spectrum. These are the spectral values, whatever you get, magnitude. You can put it in dB or just normal. So Sn e to the power j omega. So spectrum. So it's a three-dimensional plot. So it's a three-dimensional plot. So Sn e to the power j omega. It's a function of n, the frame number, and it's a function of omega. It's a two-dimensional function, but when plotting, it is a three-dimensional plot. You need the z-axis for plotting the values of this. Now, this kind of, I need a three-dimensional function like this. You can put it in an image form. Okay, you can put it in image. So what you can do is, instead of plotting like a three-dimensional, using a three-dimensional plot, you can use time axis here, you can use frequency axis here, and you can color code it. For high, you have all the numbers. Then instead of plotting this in a matrix form, basically you put it. Then you can use a heat map, means different colors representing have different values, or you can use standard grayscale, which is traditionally used. So in traditional spectrogram, this is called a spectrogram. So in traditionally, this zero means is for high values, and there's high some value give 255, let's say, for your low values. So 0 to 255, you put a range and you inverse map it. Basically for high values, you put it as a 0 means black color, and for low values you put it as 255. So on a white background, basically you will get black marks. But nowadays, of course, we use heat map. So different colors, red will portray the most amount of energy or amplitude, and then other lighter colors will portray less amount of energy or amplitude. So this three-dimensional plot we have, that we get from short time Fourier transform, we can represent it in terms of an image with time as the x-axis, frequency as the y-axis, and intensity color mapped to a heat map or some other color map or grayscale, black and white. This is called a spectrogram, and it's a very useful and important tool for visualization in speech processing. So let's see a spectrogram. So this is the signal, a speech signal. Frame by frame analysis has been done. We have time, x-axis, frequency. It is mentioned in kilohertz, converted in analog form because it makes it easier to understand. And we have this kind of here a heat map has been used, a color map, heat map. Okay, we can also have used the grayscale, but this is now a functionality offered by all softwares nowadays, so we are using it. So now here, two very important things to note. There are two spectrograms. Why? This is called a narrow band, and this one is called a wide band. And it depends on the width of the main lobe of the window, width of the spectrum. Okay, the spectrum width of the window. used. So here the window length was time domain. I'm saying that the window length was high in narrow band, and hence the spectral, oh sorry, this is the case for the bottom plot. Okay, this is the case for the bottom plot here in this case. So the window length used was high. As a result, its its bandwidth, the main width of the main lobe of the window was small. As a result, when you do short time Fourier transform and this use this spectrogram representation, you will see some vertical lines. Now you can use these vertical lines are representing the harmonics of the pitch, and you can count the number of vertical lines in, let's say, within a particular frequency range, let's say between 0 to 1 kilohertz. If there are 10 vertical lines like that, okay, here it is more clear. This region, I will use another color maybe. This region, it is more clear. So you can count the number of pitch harmonics and then get an estimate of the pitch period, pitch frequency, and hence the pitch period. Now this one on the top one, here what they did, the length of the window was low, time domain window. As a result, the beam width was high. So the short time Fourier transform was used to estimate, to find out, it gave actually a smooth version of the spectrum. You can find the formants with it. So here below there was vertical, this is horizontal line. Here you will see some vertical lines are there. Okay, these vertical lines are there in this case, and if you see over time, there are certain regions, very dark regions are there. These are representative of the vocal tract resonances, how the vocal tract resonances are changing over time. Here, for example, this is most probably F1 for the first resonance. Okay, the second resonance and third resonance, they are probably very weak resonances, and hence you cannot see them properly. But in this region, whatever sound was being uttered, A, here the vocal tract, both the first and the second formant, you can easily see. So this is how the spectrogram is used as a visual tool. It is based on the short time Fourier transform. It is a image representation of the short time 3D plot of the short time Fourier transform. So to wind up, I think this is what I was trying to say. So you have here, if you take a long window where you can see multiple pitch periods, this is a long window, you can see multiple pitch periods here. It will result in these horizontal striations. Okay, your small main lobe width, these horizontal striations you will see, these are indicative of your this omega naught, twice omega naught, thrice omega. These are pitch harmonics, and if you can see within a particular region how many count, you can count the number of these horizontal lines or striations are there and get an estimate of the pitch frequency. The opposite happens in case of, see, if you take a small window here, see, this only small window is taken. As a result, this width of the main lobe or the bandwidth of the main lobe is high. As a result, the spectrum is like averaged, and you can see the formants clearly. See, you will see vertical striations, vertical lines in the spectrum if you observe closely, and you can track how the formants are changing with respect to your speech sounds or in the speech signal that you have uttered. So that's a lot of information. I hope please go to the lectures, maybe because I am uploading the lectures already. You can again rewatch it, and will not resume any further. We'll stop our lecture here.